Hey, what's going on there? In this video today, we're going to be building an antimicrobial resistance pipeline. And we're going to be performing a lot of things in today's session. Now, building from what we've talked about, the theories we explained in our last video, what we are going to be doing today is something that is going to be really beginner friendly because we're going to ensure that all the explainability features is clearly outlined. I'll start by training the model using three separate rules. I'm going to use the logistic regression, I'm going to use decision tree classifier, random forest classifier, and I'm also going to be performing a pipeline scaling in this particular project. Also, I'm going to show you how to save your model and also how to save your data set. So if you're actually a beginner, I think this is the right video for you to watch. All I enjoy you to do is to like this video, share it, and do subscribe to this channel because that means a lot to me. To get started with this project, the first thing we would start with, we've created a file, and I've just created this antimicrobial resistance project file, and I think that not really difficult to do. Basically what I did was I just named it interactive Python notebook. I think I can delete that and do that again. amr underscore project dot interactive Python notebook. So basically what this is an extension for the Jupyter notebook that is being used here in VS Code. Okay, all right. So the first thing I'm going to do right now is the next thing is to select our kernel. I'm going to choose the Python environment because that's where all our code is definitely going to be executed. And I want to also point out some of the things we'll be working on in this project. I've actually constructed exercises with respect to the AMR pipeline project that we'll be working on right now. And some of the things we're going to be doing is that we're going to be explaining in details some of the parameters like confusion matrix, accuracy, recall score, and a lot of them. But we will not really go so deep. But at least if you're watching this video, we'll make sure you get you get a solid grasp of the basic fundamentals and understanding of explainability in machine learning, particularly for binary-based machine learning models. And I think that is that so far. The next thing I'm going to do is I'm just going to create a markdown here. I'm going to call this the AMR, that's antimicrobial resistance pipeline. Call it the pipeline project. Okay, that's definitely what it's going to be. Okay. Now, just like I explained, I'm going to show us the exercises that we've got. I've saved it here. This prediction pipeline model, we're definitely going to start by doing our data preparation, where we're going to create a generic synthetic data set with some of these variables that we've got here. We'll define our ground truth. When the patient is infected, we'll convert our data set into pandas frame, and also we'll generate our feature engineering. Particularly my want to use classes, that's an object-oriented programming style. We'll train our model, we'll perform feature engineering. Before that, we'll train our model, and with our pipeline, then we'll perform our interpretation, and we'll basically do our features, importance, coefficients. Then we'll do our pipeline scaling, and then we'll have a reflection on if at all the model which of them did show significant accuracy and all of that. Then we'll save our I think I'm going to add another one here, and I'm going to call it but I'm going to call it saving our model. Okay, so we can just you can see save the best model. Okay, so we'll save the best model. So basically, these are some of the things we are going to be doing in this particular project. And the first thing I'm going to do, I'm just going to copy this, particularly for our data preparation. I'm just going to copy that, and I'm going to place that in a markdown. Okay, sorry. And I'm just going to, yes, this is a markdown. I'm going to keep it there. And yeah, I think that works fine. All right, so that is that for the project. Now we'll start. The first thing we're going to do now is to import all the necessary library packages that are going to be of interest to us in this particular project. We'll make sure we import them, and then basically once we're done importing them, then we can now start running our code. So the first thing we're going to do now is we're going to import Okay, I think I'm running on Markdown. I'm going to delete that and create the code session. I'm going to import numpy. So the numpy is very important as np, that's the alias. I'm going to import pandas as pd. I'm going to import pickle. This is going to be used to save our model. Now from sklen dot so the first thing I'm going to do is from linear model. I'm going to import logistic regression. I'm going to go from sklen dot. Now for our training, so model selection, I'm going to import train test plate. Now from sklen dot metrics, I'm going to import the confusion metrics. I'm going to import confusion metrics. Then I'm also going to import the accuracy score. I'm going to import the precision. Then I'm also going to import the recall score. Okay. Then from sklen dot metrics, I think that is going to be that for now. If there's any other thing, maybe we can actually import pre-processing. We'll import the standard scalar. Then from sklen dot assemble, we're going to import basically our decision. No, that's going to be the random forest classifier. And from sklen.tree, we'll import our, I think that's going to be our decision tree classifier. So basically, I'm also going to import from sklen also dot. Okay, I'm going to write that well. sklen dot pipeline. I'm going to import pipeline. So essentially, all the functions, all the packages that we need for this project, we've all imported them at once. So it means we are good to go. What we use standard scaling, we use it for scaling the pipeline. This is the pipeline function, more like the pipeline package. This is the decision tree model, and I think I'm just going to bring this down so that it's going to, yes, both of them are arranged. So for all of this, okay, I'm just going to sort them properly in line with what they are used for. And yes, I think it's clear this way. So looking at all the packages I've imported, so this is going to be used to generate the data set. The numpy pandas is used to create the data frame. That makes it very easier for us to work with data tables and data and all of that. Pico is used to save the model, which I'm going to keep basically at the last. Then the next thing is to train and split our model, and that's for the model selection method. Then for the linear model, we have our logistic regression. This is the first one we use for the training of the model. We also train it with random forest classifier and also the decision tree classifier. These both are both tree-based models. And then we'll now perform our metrics, and then we'll now get our pipeline for scaling our logistic regression, and also then we'll also perform that with using the standard scalar function, and then our pickle. All right, using this to save the best model. So I think everything there works perfectly, all in shape. So the first thing I'm going to seed our random.seed. So each time I generate this data is going to stay the same, and that's going to be 46. Now, first I'm going to do now is I'm going to create a loop, because I want to save, I want to work with generated data, synthetic data set for some of these variables, and I think basically this works well. I think I'm going to take out this so that we can always have a clear visibility of what is being written in the markdown. Okay, all right, so we can use that to like know where the differences are and all of that. So I think what we can do right there is the first thing we're going to do right now is we are going to generate this particular data set, and I think we're going to have our aim to be around 900 data. So what I'm going to do now is I'm going to create a list. So I'm going to put the records is equals to an empty list. Then I'm going to start. So the first thing I'm going to do is for I in range, which is that loop for 900. Now basically what I'm going to tell it now is I'm not going to create a dictionary which this loop is going to go over. I'm going to say row is equal to, and I'm going to have for our age is going to be np.random.random. Okay, so the age is going to be from 4 to 17. Okay, all right, if I got that clearly. Okay, just to be sure, and that's numeric. Okay, now the next one is going to be sex, and that's going to be np.random.choice. Then passing that method, and it's going to be m and f. Okay, now the next one is going to be bacteria count. Okay, so that's going to be np.random.choice. Now, so we're going to have E. coli, that's going to be the first, and then another one we're going to have is Staphylococcus aureus. Okay, if I spelled that correctly, but regardless, I'm going to have Mycobacterium tuberculosis, and what else? We can have any Neisseria gonorrhea. Okay, so this is what we're going to work with for now, and remember this row is going to loop over this list, and the next one is our gene count. So that's going to be np.random.random, and it's going to be from, probably our gene count is going to be from 1 to 10, and that's going to be from 0 to 11. Okay, we can say from 1 to 11. All right, and now the next one is going to be, so we can actually see resistance score, right? I can actually say np.random.uniform, then we'll pass 0 and 1. Yeah, that works very well. So those can be decimals and all of that. Then we can actually have prior antibiotic use, and that can be np.random.random. We can actually have it between 0 and 2. That can actually be 0 or 1 and all of that. So I think that works very well. And then the next one is going to be hospital exposure. Okay, so it's going to have np.random.random 0 and 2. And then the next one is going to be region. Which is definitely going to be categorical, and that's going to be np.random.choice, and then we can pass in a list, and that's going to have probably we could see north and south. Okay, so closer, west, east. And the last one is going to be the infected, and I can actually say infected equals to 9. Okay, I think I'm just going to put a comma here, so this works very perfect. What's that? Okay, I'll close the dictionary. All right, so that's it. Now we have actually set out our record. There are other ways to do this as well. I can wrap this inside the a function, it works better. I can decide not to wrap it inside the function. But remember, the reason why we use some of these methods, approaches is so that it's easier for you to, reproduce your code. And yeah, basically makes a lot of sense. And all of that. Once you have it in function, anytime you call a function, automatically it will do what you want it to do. And that's just the idea behind programming, because programming is that you just want to make sure that the computer can do anything at the slightest call. Do you understand? Instead of you running it for a very long time, having to write so much length of code. So I'm going to save for the next thing I'm going to do right here is I think we might now want to save this particular stuff, this particular row inside of this dictionary, inside of this list. I can say records.append, and we're going to append the row. Okay. So more like we've now put this list, this particular row inside of this list. So it means that when it loops through this list once, it will save it here one, loop again till it gets to 900. And now what we now have to do now is that our infected column is not defined, but we might have to define that. So what we can say is for row in records, come on, now say if. Now what is the criteria for infected, right? Criteria for infected is that if somebody is because basically infection is going to be our target, that's going to be very massive for our ground truth. Essentially, if somebody has a gene count that is greater than 6, and then has resistance is equal to 1, and and probably has a hospital exposure that is greater than, that's equal to 0, 1, 0, rather, we can use 0, and then that means it's infected. Else, it's going to be not infected. So I think that works really very well. And so what we can do now is that we'll now write that if in our row, that's for the row now, right? For the row of our gene count, if it is greater than, let's say, like we said, 5, and also our row of resistance score, I think we're going to set that to 2, okay, because it's 0, 1, then that means, okay, and resistance score is maybe equal to 1, which is infected, and also which other parameter, because the more we keep lengthening that, or we can use the or function, we can use the or we can say our row of prior antibiotic use is equal to 1, then row of our infected is equal to 1, else our row of So I think that works. So we can just run that and everything works very, very, very well, and everything works very well in line. So basically the next thing we're now going to do right now is we will now have to we can just like step up back to what's required. What's that? It says resistance score key error. Okay, I forgot to put an underscore. That's fine. Okay, so now the next thing we need to do now is that we'll now have to now create our data frame, which is what we're going to say. We've defined our ground truth, and we're not going to convert it into a data frame. And how do we do that? We're going to call it, we're going to say df is equals to pd dot data frame, and we'll just pass in our records. Okay, you can just try to look at what df looks like, and yeah, that's just clear. Okay, 0001111 and all of that. Now the next thing we will do now is we'll now need to go back to our project documentation and understand that we now need to probably do our feature engineering. Okay, and to start our feature engineering, the first thing we'll do is to encode all our categorical variables, right? So I'm just going to copy that, and yeah, so probably I might just take this out, and I think we can just keep that here. Okay, so encode all the categorical. So when you're looking at this now, we have bacteria count. Okay, it's not categorical. It's categorical. Resistance score is numerical. Antibiotic gene, sex is categorical, and lots of them. Region is categorical. So what we might need to do now is to do what we call our encoding of our categorical. And the idea behind this is because machine learning works with numbers. Okay, it works with numbers. So if you add categorical variables there, it's not going to work. So what are we going to do now? So we have our sex encoded. So I'm going to say df. So we're going to create that particular category. So we're going to call it sex. Sex encoded is going to be, that's based on a data frame of sex, and that's dot map. So we use the map function, and we'll pass the dictionary inside of it. I hope I'm getting that clearly. I will use the double. Say m. It's going to be 1 for male, and of course for female that's 1. Okay, that's going to be 1. Then for male it's going to be 0. I think I just wanted to have a clear numbering. Then the next one is definitely going to be the bacteria encoded. So that's going to be bacteria encoded, and we'll assign that to the data frame of bacteria count dot map. Don't pass the dictionary there, and that's going to be for E. coli, which is our first. We're going to denote that as 0. For just going to look up because I just don't want to make any mistake in that spelling, and I'm just going to put that. What's happening? Okay, so I mistakenly hit the center key of my laptop, and I'm going to put that as 1. And so the next one is Mycobacterium tuberculosis. I'll just copy that exactly to reduce the risk of wrong syntax. So 2 and the comma, and for Neisseria gonorrhea, which causes gonorrhea, is 3. So basically I've encoded my categorical variable of bacteria species. Okay, and then the next thing I'm going to do now is for the df of another one is going to be region, and I'm going to spell that correctly. Region encoded. So I'll assign that to df of region. Going to use the dot map of function and pass our dictionary, and yet instead of it we'll now say okay, for north we're going to have north 0, for west 1, then for east 2, and for south it's going to be 3. So that's just basically for our region, and I think we are very much good to go. So I could actually go ahead now to create our encoding, that's our features and targets. Okay, but now what I want to do now is I want to keep my code clean, and I'm just going to create a class. I'm going to initiate a blueprint, so I'm going to call it class AMR structure. I think I'm going to say AMR structure. Yes, I'm just going to create this class, and then inside of this class I'm going to define the initializer of this class, and that's going to be self dot comma. I'm going to have my data frame. Okay, no, I don't think it's the data frame constructor. Data frame, I'm going to have my features. I'm also going to have my targets. Now, in order to get going immediately, I'm just going to initialize my some of these that have parameters that are passed inside of this class. So each time we create an object from this class, we'll have to pass all of these parameters. And now the next thing I'm going to do now is I'm going to say self dot, because it's self.df as data frame is going to be equals to my data frame. And for self dot features, now I think this is where I can actually like encode all of those that I've said, and I can say for self dot features, it's going to be, what are those features? I could call them well, I can let's just keep it here as features, and for self dot target, you can say target, not targets, is equals to target. Now this is the class I've initialized. Each time I initialize this class, this is definitely what I'm going to pass there. Now, but what I want to do now is I want to have my data frame, not just my data frame right now. I just want to kind of encode those values, state out what they are, x, y, and lots of that. So I'm going to create another method in my class. I'm going to call it the split data. Okay, and instead of this method, I'll pass self, and for this I'm going to say for my x, it is going to be equal to basically my x is going to be my self.df. Then you now have so here I can pass those things that I want. Self.df, which is my data frame. I can pass features. My y is going to be equal to self.df. Then I'll pass my target. Okay, so what this means now is that if you look at what if you look at this constructor here, right? If you look at what we constructor here that we initialized, you're going to see that we passed in our data frame, features, and target, and then we now defined it, each of these variables, self.df inside of this blue class, inside of this method. And here we just want to split our data, and what we can now say here is that each time we call this self.split or whatever, okay, each time we call self.split data, it's going to return, let it return our x, y. Yeah, x, it should just return our x. It should return train test plate. I think that's fine. And to have x, y, random state equals to 3, and yeah, we can have our test size as 0.2. I think that works fine. So each time we call this, definitely that's what it's going to return, because we can now input some kind of equality inside of a return statement, but this is just basically what it has to return. Okay, so I think that's good. We are very, very much good to go. XY random state equals to 3, test size equals to 0.3. So now the next thing we'll now do now is we'll now have to now go back to our exercise, and since we've splitted our data, and it's just basically, well, maybe explaining why we do not train and test on the same data. That's something we're going to talk about in the later part of this video. So the next part here, we're going to actually do our model training, no pipeline yet. And what we will do now is when we get back here, we can now create another method for log train. Okay, so what does log train means? What log train illustrates now is that this is for the logistic regression training. Okay, logistic training, I can call it logistic training. So I'm going to pass self as usual inside of it, and to train this we'll have our x test. Okay, now I'm going to say x train, x test. All right, about y train, y test is going to equal, so now we call this method, so we'll call it split data self dot split data, okay, and that's it. So what we have just done now is that we will now have our x test, x train, y test, x y train, y test assigned to this what splitting what this split data. So it means that this particular method here is going to split the data for us. That is each job. Each job is for us to do what? Is for you to split what? The data. Remember, that's one of the reasons why we have the train test play and we have a random state. Means that it's definitely going to split it at a particular state. If we change it to 93, it's quite the same thing because it's going to split at that particular frequency without changing anything. So the next thing we'll now do here is our model is going to be equals to our logistic regression model. We can pass our maximum iteration for our logistic regression into 1000, and so essentially what we might need to now do now is to get our model, return our model.predict, and model, we can say model.fit, and yeah, so that's it. So model.fit, I'll pass our x test, okay. No, not our x test, we'll pass our x train, y train, okay. So each time we call this model.fit, it's going to pass an x train, y train inside of it, okay. And then the next thing we will now do right away is that we're now going to we'll return the model, okay. The model, that's what has been predicted, which is this model fit, and then we'll also return all other characteristics that are quite of interest. So even if we call this function now, this class now, maybe we'll create, let me just create, if I create an object and assign for these features, what is definitely going to be inside of it. It's quite imperative for you to get that. It's definitely going to just create something like a diamond or something, to just show you the model right on the console. So I'm going to go straight now to we have some metrics that we want to return, and I'm going to now say, okay, each time we call this method, return the model, okay. So that's what definitely we want to return, this model, and then also return the accuracy score. And what's the accuracy score giving us? So you can see I can actually say model.fit is that's what to return, which the model, okay. So but the accuracy score now is denoted by our y test. So that's our y test, comma, then we'll have our model.predict. Yeah, we'll pass our what? X test, okay. So this is more like our ground truth. Then we'll now pass in that's the other splitted test size that we want to use. So it's now the margin between the ground truth and what this is going to predict. That determines the accuracy of this model. Okay, so the same thing actually happens in the precision score, which is the next thing. We might look at just a confusion matrix. So we take the confusion matrix, and it's going to do just the same formula, but just as the method for it is. So it should also return us the precision score, and also return, and it should also return the what? The record score. So I'm gonna record score. Now basically this is it for this method. I think everything works fine, no issues. We'll create another method because we are working with 3 models. We will now create another model, and this is going to this is going to be the tree train. So what we mean by tree train is the decision tree, okay, that was imported from the tree method, and that's the package right that was imported. So pass the self argument. I think I might use the double column. I'm going to say x train, x test. I want to say, I think I can just copy that line and put it there, okay. And then we have our model is going to be we call the decision tree classifier, and when I want to pass a max depth of how it's going to iterate in its decision making as 5, we'll call model.fit, and we can say x train, y train, okay. And I think that works very well, and we can now see it should return all of this. I could just copy this, okay. Okay, so type in this code again. But the next one is our next model. We're going to call this method the forest train, which is our forest, our random forest classifier, and we're going to see the X train. I think, like I said before, I'll just copy this. I'm just going to put that there, and so the model is going to be the random forest classifier. And here, what we call the n estimator, so we'll pass it as 100, and then for the model.fit, it's going to be at x train, y train, okay? And we can return the model. The accuracy score, which is going to be the y test, and with the model.predict x test. And I'm just going to copy those. Okay, all right, so I think that is that. For our training, everything is working fine. We have our train display already done for our 3 models, which is a logistic regression model. We have the decision classifier, and now the random forest classifier. Now remember, the next thing we'll now do now is we'll have to create a structure. So we can just create a structure, or we can call this the object, and we'll initialize an object. And then what we might now want to do now is to pass in our parameters. So the first one is df, which is global, and we'll now have to pass in our features. So what is our features? We can pass in our features. We can still pass in our features here, so each time we call these features here, which we clearly stated here, basically it is just going to give us what we want, and but we can still pass that features in here as a list. That works very fine, and it still works perfectly okay. But now what I'm going to do now is, I think it's going to be important for us to just kind of list our features here, okay? Because based on our other part, that's for the target is just the infected, okay? Because here we can see target is equals to infected and all of that, so that still works fine. So but it still works fine here too as well if we pass that in here. So we can say for our features is going to be equal to, so we call the columns. So what are the columns that we need for our features? So I think we can get that from, I think I could just print df. Now the reason why I did this is so that I can be able to see this. So I'm going to paste that back, and it's going to help us to see our features. So our features are basically all these parameters that we have, except this infected, which is our target. That's the ground truth. So the first one we have is our age. This next one we have is we have sex encoded, and then we have so we have sex encoded, we have gene. Okay, let me just wrap that up. So we have gene count, and also we have resistance score, and we have prior antibiotic use, and we have hospital exposure. I think we missed out something, bacteria encoded, okay? Just to make sure we don't miss anything. And then we have, after hospital exposure, we have our region encoded, okay? So I think that works fine, so we can just shorten that. All right, so this is our list, and that shows our features. Now remember, in that object you can see features is equals to features, and I think target is equals to, now for our target, remember our target is equals to infected, so we can say our target is equals to target So I think that works fine. So yeah, that's fine. So no issues with that. Okay. Now the next first thing we're going to do now is that we will now have to start calling each of these individual methods. Okay. So that's how it works. After we've initiated our pipeline, we've initiated our class, the object, and we've passed in all the necessary parameters. Remember, whenever you initiate a class, a blueprint, and you pass in all these parameters, it means that each time you call that class, you must surely do what? You must surely pass them in. So now what we'll now do now is that to call the method now for training our logistic regression. So what we might now do now is that since it's going to return model, accuracy score, and all of this, what we'll now do now is we'll now see, now watch, we'll now do logistic model. It's now going to be equal to, because this is what is going to return each time we call this logistic stuff, because we can call it, we can just call it here and it will print all the output. But what we want to do now is I want to make it very explainable, right? So logistic model, then the next one is accuracy score. I'm going to call it logistic. Accuracy. Then the next one I'm going to call it logistic confuse. This is for the confusion matrix. And then I'm going to call the next one logistic. I'm going to put on the score, precision, and then next I'm going to call it logistic. The next one is logistic recall. Okay. Now it's going to be equal to, I'm not going to call that method structure dot, which is this method now, which I've initiated the object now. So it's now each method I call now, it will do what that is contained inside of it. So I've now called structure dot logistic train. So automatically that's going to run without any issues. Okay, so what do we have? We said bacteria encoded gene is not an index. So I think there's an error. Okay, I forgot to put the comma here, and what else? You said not enough value, got this expected to 5. What is the issue? I think there's somewhere there's no comma. 1, 2, 3, 4, 5, and here we have 1, 2, 3, 4. I think there's something missing. Okay, yeah, we missed out on precision. Oh, sorry about that. I'm just going to add that. Sorry, I'm just going to put that. I'm going to call this precision score and put a comma here. And yeah, I think that should work perfectly fine. Okay, and we could just put that. And yeah, here we go. So it works very well, and that's this. Okay, I can work the whiles past and array, so that doesn't really matter. We can actually use our .ravel values .ravel, but that's by the way for now. And what we can do now is, since everything works very perfectly, we can now do now, because I'm going to do the explainability of this model. Essentially what I'm going to do right now is, so we're now going to do now for the accuracy of the logistic model. So we're going to actually work for the accuracy. Then after that, I'm going to do for the confusion. I'm going to explain the confusion matrix. Then also next I'm going to do now is I'm going to explain the precision score, and then the last one is going to be the recall score. Now what we'll do now is we'll have to now print out all of those. Okay, so the first one I'm going to do right now is I'm going to print, I think I can keep this without indenting. That's what I'm going to print for the accuracy of the logistic model. So that's going to be, so we'll just call the logistic accuracy, of course. So we call this, okay, so this is for the accuracy here. That's the second one. Good. Now the next one we're going to do now is we're going to print again. So we'll print now for the confusion matrix. So for the confusion matrix, we're going to print logistic confuse. Okay, now we're going to print now for this precision. So for the precision score of the logistic model, we're going to print logistic. I think we okay, so we're going to print the logistic precision, and that's that. I think that works fine. Okay, I think I'll just send this in, that semicolon. And the last one we're going to print out right now is I'm going to print the recall score. So to print the recall score, so I'm going to print logistic recall. I think that works. That's fine. Okay. So that works fine. So I'm just going to print this, and exactly, we've got our logistic regression model. So basically, I think this is it. This is what it is. And I think I'm going to run an interpretation of this. We can just tweak our data. We can change the seed to 8 and see. Okay, nothing happens. That works perfectly still. We can just tighten the, I think I can, it's perfect. So I just want to tighten, let me tighten in this. I will change this to and I'm going to run that. Okay, what's saying? Needs 2 classes in the data. It contains only one. NP dot 64. Okay, I think that's fine. What if we work with just this? Okay. Okay, more like it's giving us some stuff. I can just take this to 18. So I think we can just leave it this way. Okay. All right. So we can leave it this way. All right. So now what we are going to do right now is to perform what we call the interpretation of this model. All right. I wanted in a scenario where we might have like 0.99 something, but everything looks perfect. So what's this particular what the interpretation of this means now is that I'm going to use a markdown here. I'm going to use a markdown. So what I'm going to do right now is in this markdown, so I can actually say that what I'm going to say here now is that for the accuracy, right? For the accuracy, what it implies solely is that what this result shows now, it shows that the model showed 100% accuracy in its prediction. Okay, all right. And the next thing there is, after the model showed that, then we'll now look at what we call the confusion matrix. And I'll think about this confusion matrix. We have 94, 0. We have this kind of 2-dimensional array here. And what it means is that we have something like true negative. But this is something that's usually used in epidemiology. We have false positive. We have false negative. And we have true positive. Now, let me take us back a bit to what I explained about this. Okay. Remember, here is 94, 0, 0, 86. So, if we go back to my previous lecture here, I did mention that for your confusion matrix, we've got true negative, false positive, false negative, true positive. And what true negative means is those people that were accurately diagnosed to have the disease. Okay, which in the case of our data here, we have 94. Okay, so that means 94 people were accurately diagnosed not to have the disease. That's true negative. Now, for false positive, it means people who were wrongly diagnosed to have the disease. That's false positive. Now, essentially, for false negative, which is very dangerous, it means that people that have the disease, but they were flagged not to have it. And for true positive, it's people that have the disease and were accurately predicted to have it. So that's why we actually have some of these parameters here, which I'm going to still explain. So what this implies here now is that from based, now this is for our confusion matrix, right? So I'm just going to put that mark down. Confusion matrix. So since this is for our confusion matrix, so based on the TN, that's a true negative, it shows that 94 people or specimens or data or whatever thing, participants, anything that relates with your data. So you see 94 people were accurately predicted to not have the condition, or not be at risk, or be, if I'm measuring risk, or whatever. Now I'm going to go ahead to say based on FP, which is 0, it means that 0 people were wrongly predicted to have the disease, whereas they don't. So that there's no need for that whereas. So because we are wrongly already satisfied that terms. Okay. So I'm going to say based on Fn false negative 0 people, we are wrongly predicted to not have the disease. And that's going to be what? That is more like, yeah, so that's just it. So it's very dangerous, that one time. Now, let me talk about the last one before I go back a bit to this accuracy to explain what the statistical measures to calculate that. Now, essentially, what this means now is that for your true positive, it means that 86 people they are accurately predicted to have the disease or condition, whatever. Now, statistically, to calculate for your accuracy, you can actually say true positive plus your true negative over or divided by the sum of the true positive plus true negative plus false negative plus false positive. And that's going to give you 1.0. So to check that, we'll see we can have in a situation whereby we just got only our confusion matrix, it means that we can still essentially calculate or account for all these other parameters that we've got here, and that is going to give you 86 plus 94. That's 86 plus 94, and that's going to give you about 180 or thereabouts, if I'm correct, if I did get that correctly. And then 0 plus 0 plus 0, 86 plus 96 is the 180, 180, that's 1. So that's it. That's how we got to 1.0, which is 100%. Now, when we talk about precision here, precision score for this logistic model is 1.0. And what that implies is that if our precision score is 1.0, what it means is that for every time the model predicts someone to have the infection or disease, it is what? 100%, which is 1.0 accurate. And that's something we can easily calculate by saying our true positive all over the sum of our, that's the sum of our true positive plus false positive. Remember that false positives are more like people that were wrongly identified to have the disease. So that implies that if it's 0, so that shows you that automatically there is 100% accuracy. You understand? So, and it's something that is important for one to note, particularly in public health. Precision score is quite important because we have to make sure that it's very precise, because if it's not precise, we might waste a lot of resources, which is managing people that don't have the condition, whereas the result is showing that they have it, and then that's waste of resources. So it's very important for precision. Precision is important in resource management and all of that. Now, another thing we might need to look at now is what we call the sensitivity, which is the recall. We're going to call this the recall score. So for everyone that has the disease, how many were the model able to catch? So this is very important, okay? People that have the disease and that the score is 1 is something that is very important, very, 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 very important, particularly in outbreak, in terms of public health outbreak detection, because if we omit cases, and that is something that can be very dangerous. So our recall score is something that is very pertinent, and that's actually given by our true positive all over our true positive plus our false negative. Okay, so false negative are actually people that have it, but the model is showing that they don't have it. So when in this case we have our we have 86 over 86 plus 0, and that's 1. So that's actually 100%. So it means that our recall score is very high, which is 100%, and that shows significant success. So this is actually this is more like the explainability of this particular model that we've run, because in the next course we're definitely going to run for a lot of models and all of that. Okay. I just try to tweak the data set, to see how I can come up with lots of stuff and all of that. Gene count greater than 4. Let me just put it greater than 7 to see if it's going to change our results, and it doesn't seem to. And so that's just basically that. Okay, and yeah, I just want to make everything. Yeah. So the next thing we will do is we might want to look at our. Because of this markdown, I'm just going to run my next code, the next line for our tree-based model to check the accuracy of that model. And what I'm going to do, I'm just going to copy this as well. I'm just going to change this to tree, and I'm going to change this again to tree to save my time. I'm going to change this to tree. I'm also going to change this to tree. Okay. All right. So I'm going to call this our tree model. I'm going to call this as well. I think we can see 3 and record score for 3. And now we'll now change this now, because one of the things we might need to know is to now say, okay, for our tree, remember tree model, I think it was very important for us to call all our models here, just like we did here, okay? And more like just initiate it so we can print all of them. So we can actually write that here. We can see our tree model, then our tree accuracy, then our tree confuse. Okay, I'm going to say our tree precision, then our tree recall is equals to the method structure dot tree train. Okay, and that works perfect. So I think we can take that, and so basically I'm just going to remove this. I'm going to say tree arc, just to be sure. Oh, that's an issue. I don't know why that didn't run through, but I think I'm just going to bring that closer. Okay, sorry, that works fine. I'm separating this with some kind of markdown. I'm just going to go up a bit. So I'm going to run that, and that's working fine. And okay, I think there are some things that are not defined here. So I can say call this. I'm trying as much as possible to make my syntax very short. So this is going to be 3. So this is going to be 3 record. Okay, so we're going to run that, and as usual, it returns a very perfect accuracy of our tree model. So I think yeah, so this is just basically how it works. The same interpretation works as well, but we might just need to go through this data set. We can see how we can tweak in some things to see basically how we can, yeah, basically just get something out of it and play with that. So for our target of infected, I can say 2 if it's greater than or equals to 5, and rule of resistance score, I think I'm going to drop that. Let me drop it. On prior antibiotic uses this. Let's see if anything changed. Yes, I think this works perfect. I think I want this now, so I just dropped that. So yeah, so it's same thing. It's applied. Same thing applies still. We have our record score now to be 97% after I've made some kind of changes in for our logistic model, and our accuracy is 0.9944. So what it means here now is I can basically update it, and I will say here, okay, let me scroll up a bit. So I can see here that this is going to be 99.4, okay, and so that means, so this is going to be, remember to calculate our model accuracy. That's it. That's our logistic regression accuracy. We'll have 113 plus, okay, so that's 113 plus 46. Okay, that's all over the sum of 133. I think, oh, sorry, forgive me if I can see that one. 133 plus 1 plus 46, then plus 0. So that's definitely going to give you 0.96. That's what's going to give you if you put that in your calculator. It's 0.99 rather. Okay. All right, so it means that our confusion matrix is going to change. It's no longer going to be 94 people who were accurately predicted to not have the condition. So it's going to be 133 because the data set changed. Therefore, our false positive is 0. So it means that we're definitely going to have a very high precision score. Okay, and yeah, for our false negative we have 1, and that's going to drop our recall score slightly by 97%. And that is for our true positive, it's now 46. And yeah, so basically that's just it. And yeah, so in terms of our precision, 100% maintains that recall score. It's now going to be 97.8%. Yeah, if I could spell that correctly. Yes, I think that works very fine. So this is just me tweaking and just to get out some stuff. So I can decide to change another thing again, another. So if I run for this, you see that the accuracy of our model for our decision tree is much more higher. So that's approximately 100%, and the interpretation is still the same. What it means here, I can create another markdown, because most times repetition makes it easy to understand. And what it means is that the accuracy, it means that the model accuracy is 100%, right? It's 100%. That means accurately it's made a very great prediction. For the confusion matrix, it means that 133 people were accurately predicted to not have it. Okay, that's true negative. Okay, and then it means that 0 people were wrongly predicted to have the disease. Okay, or infection, whatever. Okay, I think more infection is what we're going to use. And okay, so that is what we call false positive, and it means that 0 people, so meaning that our recall score is about 100%. 0 people were wrongly predicted to not have the infection. Okay, that's false negative. Okay, and then for the last one is going to be our 47 people were accurately predicted to have true positive. So this is the information that we basically need, and I think I can just do with this markdown. Definitely, I'm going to drop all of this code in my Git repository for you to explore and get the very best out of it. And I think here we're going to look at the forest tree classifier, and that we're going to say for forest model. Don't say forest accuracy. Don't say forest. We'll call the forest confuse. We'll call the forest precision. We'll call the forest recall. We'll take it to structure dot forest train. Okay, so we'll call that method, and now we're going to say to print accuracy of the. So let's see how it's going to perform. Okay, forest model. So we'll call the forest. Okay, then we can print. Now to get the confusion matrix, we can call it forest confuse. We can also print. We can print the precision of the forest model. I think I'll call that forest size, and then the last one is going to print the cost score of the forest. I think I'll call that forest model, and that's forest. That's going to be the forest. So basically, if I run this and yeah, so it gives me a very perfect model. So that's just how it works. Remember, this is your data set. You can try to tweak it how you want. I can try to change this to 98. At seeds 98, what does it give me? Okay, it gives me another stuff here. Now it's now logistic is now correct there, and I think I can just one of the things I can just do now is again I can tweak my. I remember this is not a real data set, so I can just add. I can add and probably we can see and maybe I'm not going to restrict to region. I can say hospital and the rule of okay, I'm going to turn that well. Hospital exposure is equal to 0. Now let's see what happens. Oh my goodness, I love this so much. Okay, so it draws our model again, and here we have 98%. As usual, we can change that. Remember when I did change it, and yes, I'm just trying to try several parts of the data set to see several parts. And for the tree, what happens again? Accurate for the decision tree, which is very great model, and for this too shows some accuracy as well. So basically, all the interpretation that we have for this is also going to apply. Remember, I changed this, so this has now changed. Okay, so here now it's now going to be 154. Here is going to be here is going to be 26 and 00 as well, and all of that. So I basically changed that, and yeah, same thing actually happened in my logistic regression. So it's just something very important for you to note here. We're now having two false negative from this particular data set. So what that means is that this is now our record score is what? Our record score is 92.3, and our precision is 200, and number of people who were accurately predicted not to have the disease is now 154. Okay, so that's all you can find here, and is 154. So here is going to be what? False negative is now 2, and this is 24. Okay, so yeah, so this is actually basically the formula of calculating that for that. And yeah, I just wanted to understand, I'm just playing with the data set. You can also download this and also make changes, put in your own description and all that. So far from this training, we can see that we have a random forest to be very, 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 very random forest on our decision tree to be very precise and accurate, and showing a very good accuracy in the model. So the next thing we're going to look at now is that I just want to save this model, but we've done our model training, we've done our calculation of our confusion matrix and all of that, and we've done the interpretation, we've explained recall. I've told you why recall is important, disease discretion, and what high precision means, which I did explain. Now we're going to actually look at some stuff we call the feature importance. Particularly, we're going to extract. I'm just going to copy this. Okay, so I'm just going to copy that, and okay, not here. I'm jumping into this place. Now I'm going to create a markdown, right? And here now, what we're going to do now is that we're going to actually do a feature importance for the decision tree and random forest. Okay, it's not something very difficult. It's something very simple, and there's something called the feature importances, which is something we're going to use to do that. So the first thing we're going to actually do now is that I'm going to do for the tree. I'm going to go for the tree importance. So I'm going to assign that. That's for the tree importance. We might more likely assign that to a data frame, where we can now, I can say tree importance df. So I can now assign it to pd dot data frame. Okay, and what I want to do right now is I just want to pass in Like I'm going to pass in a dictionary as usual. Now remember, I'm trying to get the importance for the decision tree, right? So I'm going to say for feature, just give me the, probably I want the features, right? Because I want to get the importances, right? And now I'm going to move. The next one is going to be for the importance, which I'm going to explain. Then let me have that's the tree. So that's a tree model, okay, dot feature importances, okay. So this is the tree model, okay. So we want to know the importance of this particular model. So what do we mean by importance? We're trying to look, it usually ranges all the values. When you sum all of them together, it's going to give you 1. So we want to know more, like think about it like which of the features. Now when we talk about the features, remember we're talking about these features here. I'm going to scroll up. This, talking about this. So we want to know which of these features have a significant impact, in the model's training. Just think about it like that. Just like the way you talk about the coefficient, although that's more like the directionality of impact and all of that. But in terms of features, we want to know which of them has more magnitude, or kind of in the training in the model prediction of all these age, sex, bacteria count, gene count, resistance score, prior antibiotic, hospital exposure, and all of that. So that is just basically what we want to know. And to do that, the first thing we're going to do is we already have this. I'm just going to say probably tree importance df again. I'm still going to assign it now to sort. Yeah, probably I just want to sort it. Or what I can do, right? I'm going to print tree importance. Okay, let me close down. Now dot sort the values. Okay, dot sort values by equals to the importance. Okay, I want to sort it by importance, and so I think that is just that, and you can say ascending equals to false. Okay, and yeah, let's print that. So but if I don't want this particular indexes to show, what I might do now is dot to string. Okay, I'll pass index equals to false, and that definitely goes on. So what this means now is that based when we trained this particular data set using the decision tree classifier, it means that this is the hierarchy of the importance. So it means that gene count showed significance importance, you understand, compared to all of that, you understand. So that is just what it is. So when you sum it up, it's definitely going to give you 100. Okay, sorry, 1, not 100. I just made a mistake. And that is that. I think I just want to increase the age a bit to 90, and I think nothing really happens. What happens is that the confusion matrix has now changed again. We now have I keep changing this. We have 147. Okay, and that's how much I wanted to play with it. I'll have 147 in our first negative, in our true negative, and here we have 3, and here we have 30. Okay, so that's now going to be 98.33. Here is going to be 90. That's our recall score, 90.9, 90.9, and that's for recall score. For accuracy, it is now going to be 98.3. Okay, all right. So now the next one, if we run that here for our tree model, our model has accuracy remained the same, but here rather we have more like we have 147 people and 33. Okay, all right. So that works. And if we do the same thing in our forest, Nothing still changes. Really serious. We have. I think that's still it. Okay. We have for random forest. We have 147 and 333, which is true positive. 147 being true negative. So all right, that works fine. If we now run that again, therefore it should change some values here, and this is basically what we call the feature importance. Now for us to do the forest importance, because this is actually very important, forest importance is equals to pd dot, we'll pass it in the data frame so that we can be able to visualize it. I'll pass in the dictionary, and inside of that dictionary we're going to have our feature, and we'll have it to compare to features. And also we'll pass in another of our importance. We'll have now our forest model dot, yes, that's dot feature importances. Okay, I think that was feature importance. Is there any people that didn't spell correctly? I think I'll have to use a double importance forest model dot feature importances. Okay, I think that works. So for us to print that, we're going to print forest importance data frame dot sort the values. So we're going to sort the values. So we're going to sort it by, so we're going to sort it by importance. Then our ascending, I'm just going to spell that correctly, is equals to false. Yeah, I think I can leave that. So I think you see there is a difference now between the importance here and there. Here, you see that the G for decision tree. Okay, so this is for the forest. I'm going to write that out clearly. So this is for random. I'm going to say random forest classifier. Okay, so this is the feature important for the random forest. So what you need to understand here now is that the feature here, it actually have other parameters that are showing significant impact on the features compared to that of the decision tree classifier here, where you have gene count. Okay, and that's actually very important for you to note. Okay, so here is the decision tree classifier. Okay, all right, so that works fine. So that's fine. So compare, you have prior antibiotic use, and there you have we have gene counts. Okay. Now the next thing we are going to do after we've gotten the feature importance, we're going to actually initiate a pipeline for scaling. Quite important, and particularly for our logistic regression, which is saying 98.3% after we change some things in it. So we want to know if there are some probably some factors to put into consideration. But before that, we might want to undo the coefficient, understand the directionality in our logistic regression. Okay. Yeah, so that's the next thing we're going to do. So we're going to check our exercises that we mapped out, and we say the logistic coefficient. Okay, so before we build that pipeline, and so what we're going to do right now is we're going to actually paste this. Okay, so we're going to actually do for our logistic regression coefficient. Okay, now what we can say is our log. Now we can say for our logistic coefficient. Okay. So we're gonna assign that as usual to a pandas data frame, so I can be able to see that. And because we can't do a feature importance for a logistic regression, rather we'll have to use we'll have to do a more like a coefficient, right? Because of it's basically we want to just use it to understand the magnitude of effect. For tree-based models, they usually use what we call logic. Do you understand? And it is just only in the case of a logistic regression or linear regression that we might want to understand the directionality of the coefficient. So yeah, the tree-based model, they use logic in making decisions. Okay, all right, so fine. So we're going to pass the dictionary inside of this, and then the next thing is going to be now is that for our coefficient is going to be our features. Okay, so those are actually what is going to pop out in our as our coefficients. Okay, fine. And then for our, okay, so that's, now I think we might want to just correct that. This is going to be our features. Okay, feature, that's some of what's going to pop. But then for our coefficient, I don't know if I spelled that correctly, and I think I was thinking of. So our coefficient, that's for each of them. Now we're going to actually have our log model. Okay, then we'll put dot coefficient. Now we might need to pass as this thing 0 inside there because it's a one-dimensional array. We just want to get the first array, that's okay, that's the first row. Okay, that's what basically what we want to get. So we can actually just do our same thing. We can actually print our I think I can call this our log coefficient data frame because we cannot print our log. Let me just use a shorthand here, okay, to be the syntax rules. So you can see the log. Okay, then we'll now put a dot sort it. Let's sort it by values, and then we can actually put something like, okay, we want to sort it by the, so by equal to by the coefficient which we did assign here, and we'll have something like, we can actually pass args, right? But I think we can just pass, say, ascending equals to false, and then that's it. So yeah, basically, so what this means, what this implies is that basically what this implies that it implies that, now I'm going to go back here now to explain something. Now when you go back to these basic definitions that I have here, I did mention that if it's negative, right, so it means that it reduces the risk of the target, right? And then if it's positive, it increases the risk. Now we're actually going to apply the same logic here, and what this means is that based on our logistic regression model and the directionality of the effect, for minus 0.001088, it means that looking at the number line, I can actually check out the number line, which I did illustrate here. So that's going to be around slightly here. So that's more like it actually have a slight effect in reducing the risk of antimicrobial resistance. I'm just going to split my screen so we can be able to see that clearly. So that what it means. So if you look at it here, for age, that means age slightly reduces the risk of what? Antimicrobial resistance. That's what it means. So for bacteria, it means that bacteria slightly 0.1, that means it's almost at here. It reduces the risk. 0 is the line of null effect. And for resistance score, it does slightly reduce. That's going to be here, but age really has a minimal impact because it's 0.0, but compared to hospital exposure, that has a very significant impact in reducing the impact of it, has in reducing the infection, antimicrobial resistance effect. And it's something that is true. It is just true, because once you're going to the hospital, there are tendencies for you to have reduced risk of antimicrobial resistance or reduced infection. Okay, and also they say prior antibiotic use also exposes the risk to the infection. So it means that this one increases. Okay, it increases the risk significantly, very significantly. And that's one of the things we need to understand in using coefficients for explainability in logistic regression model, is that it just helps us to understand the direction of effect. So just look at this number line, picture it as as that line of direction. So it's going to tell, okay, this is increasing, this is reducing, this is at the line of null effect, and that is just basically what it is. So for prior antibiotic resistance compared to region, it means that region has almost no significant impact on impact of antimicrobial resistance or whatever. Now, there's something I'm going to explain right now, which is important, particularly in logistic regression, which is what we call scaling, because it is very important for us to scale our data. So scaling our data is one that is quite very important, because the magnitude of our features can actually have an impact on how our model is being trained. And that's why the reason why for models like logistic regression, k-nearest neighbors, support vector machine, and some of them, it's very, very important for us to scale our data. So scaling our data is quite very imperative because it basically makes us to have more precise estimate of our accuracy. And that's what we're definitely going to do here. And that's what some of the things is definitely going to be the last thing that we're going to, part of some of the things that we're going to do. That's for part F. And we're just going to actually say why scaling essential. Scaling is not done in tree-based model because it uses logic. Each time it splits the data, whatever thing it splits it to be will remain at that. But compared to logistic regression, where there could actually be changes due to the magnitude of the data, and that's some of the things we need to understand. For tree-based models like randomized forest classifier, decision tree classifiers, and some of the gradient boosters and all of that. We don't really apply scaling. Okay, the grad boost we don't really apply scaling, but for randomized for KNN, then all of that requires some kind of directionality, we do apply scaling. So we're going to actually build a pipeline. We're going to build a pipeline, and that's the next thing I'm going to do. And one of the things I'm going to do now is, I think we already created a markdown for this. I'm just going to copy this and like basically I'm just going to create a markdown and put that markdown here. And essentially, so what this means is that inside of this markdown, we can now say, okay, since we're trying to build a pipeline that includes standard scalar, logistic regression, and so remember we've already imported, so we did import from sklen.pipeline, we imported so that's from, we imported import pipeline, and from sklen.preprocessing, we imported what? Our standard scalar. Cool. Now what we're going to actually do now is that we're going to actually create this our pipeline. So I'm going to call it a pipeline. It's going to be equal to, and I might say here, I'm just going to call the pipeline constructor. I'm just going to initiate that, and inside of this, I'm going to pass steps. Steps is going to be equal to, I'm going to pass this, and I'm going to pass another tuple, and instead of this, I'm going to call this scalar, and it's going to be the standard scalar, and we can actually have a comma here. I can actually have our another one here. We can call this our model, and it's going to be the logistic regression. So we're going to actually place the maximum iteration at 1000. Now, essentially, what this is trying to do now is that we want to scale the logistic model. So what we can now do now is that since we've actually initialized this pipeline, and this is now what the model that we are now going to use here, we can now start by saying X train. So we can say X train. So already we have so we're going to actually train, the pipeline. So we're going to train the pipeline. We're going to want to train the pipeline. Okay. So we're going to say X test. Okay. Y train, Y test is equals to, now, because we want to actually train the logistic regression model, we might need to call that function, that method, and that is in our structured dot logistic train. Okay, and I think that works fine. So the next thing we might now need to do, since this is for our pipeline, right? So I just hope we're correct, and we've called this, and now the next thing we'll now do right now is we're going to call the pipeline dot fit. We'll pass our X train, Y train. Okay, and we run that, nothing happens. Oh, I thought you said too many values to unpack, expected 4. What is the error? Okay, I think this is supposed to pass a pipeline. No, sorry. Okay, no, this is not what we'll call yet. Not the logistic train. I think that was a mistake. We'll call the pipeline dot. So we'll go back to we'll call the method for our split data. Okay, dot split data. All right. So this is going to be structure dot split data. So that's it. That works perfectly. So this is our pipeline. And also the next thing we're going to do right now is we're going to do our pipeline.fit xy extreme. So for us actually to now get the accuracy of our pipeline after passing our logistic regression through the pipeline, it's very important for us to understand the code. And what we're now doing now is we're going to do something like our y breads is going to be equals to our pipeline dot. So what we can do now is we can call dot. So we pass our predict, okay, pipeline.predict, and that's going to be our x test, okay. And now the next thing we'll now do now is to get, remember this is for our prediction, this is our pipeline prediction, okay. And then what we'll now do now to get our pipeline accuracy, we can also get our pipeline confusion matrix. We can also get our pipeline precision score. We can get our pipeline. We can also get our pipeline. Probably we can say our pipeline recall score. That works fine. And so we're going to actually use the same syntax. What we'll do now is for. So we're going to just print that straight away. So we're going to print. So that's to print our pipeline accuracy. We're going to say pipeline accuracy. Okay. So this is what it is, and we're now passing our accuracy score. Remember, we did import that at the beginning, and instead of it, we'll have our y breads, okay, and we'll have y test, okay. So I think I can just take this. Sorry, I just want to save that so it doesn't go out of there. So this is going to be our confusion matrix. So I'm just going to pass that method, confusion matrix. That works, and I'm going to separate our. I think I can put some sort of pipeline confusion. Okay, so that makes it more readable. Let me just copy this. So we're going to call the pipeline precision score. Okay, so this is basically what tells us how accurate every time it predicts someone to have the disease or the infection. So this is going to be our recall score. Sorry, mistake. Pipeline recall score. Okay, that's the method. I think that's fine. So everything works perfectly. So we're just going to print that, and I think you can see that our pipeline, everything has now probably been scaled, and the accuracy. So I can actually use the markdown here, so I can say that the accuracy for our pipeline, for our logistic regression pipeline is that's the accuracy is 100%, and based on the confusion matrix now shows 147 0 0 33, and that is that for true negative 147 people were predicted to not have the disease. That's after it was scaled through the pipeline. Okay, so we can still, and also was also to have the infection where accurately, I'm going to say accurately predicted not to have the infection as antimicrobial resistance infection. Now for false positive 0, so that's 0 people were wrongly predicted to have the infection. Okay, then for false positive, for that false negative, it shows that after being scaled using the standard scaler through the pipeline, 0 people were predicted wrongly to not have the infection. whereas now for the true positive, it implies that 0, no, that's 33 now, people. We are accurately predict to have the disease. Okay, so that's true positive. So this is actually very important for you to understand the pipeline. So the pipeline precision score was 100%, meaning that each time, so that's pipeline precision score was 100%. So that signifies that each time the model predicts one to have the infection, it was 100% accurate. Okay, and now for the pipeline recurse score, it was 100%, meaning that the model got 100% of those that have the infection. Okay, so these are actually some of the things we need to understand for pipeline, and basically I think they are really quite helpful and quite important. So the next part of it is that we're going to be saving our data frames into CSV. I'm going to show us how to do that. That's definitely the next thing I'm going to do, which is H. Then we can now, like, did scaling improve or reduce the model accuracy? I think it improved the model accuracy. Can scaling sometimes reduce accuracy but still be correct? Of course, surely, because the idea of scaling is to make sure that there is kind of standardization of the measures. Okay, in NumPy you can actually use some kind of functions, like there are some kind of functions to actually measure the variance of the features, to make sure that the features have some kind of balanced measurement. Okay, so it wouldn't affect how the model learns from data. Okay, so this is actually very, very important in machine learning. And which model would you choose for real world? I'm going to choose the decision tree, of course, because when we look at the decision tree here, if we have a look at decision tree classifier, we're definitely going to see that, yeah, it's really it really performs really well, as well as the forest random forest classifiers. So performed exceptionally very well doing this scaling and model training. So the next thing we're actually going to do now is to save the model. So I'm going to show you how you can save the model and also how you can save your data to CSV. That's comma separated value. So we're looking at saving the file, all the files. So what files do we have here? We have our features data frame, we have our main data frame, that's data frame DF, and we've got our coefficient data frame. So we might want to save them to CSV, probably use them for any other feature. Probably you want to run a meta-analysis with some of the parameters from there. These are definitely what you might want to do. So now to save your data frame, that's the main data frame. Now to save it as a comma separated value. Now what we're going to do now is df. Now we pass df to CSV. Okay. Now we can now call the name. So now anything you write here now is what it is. So df was assigned as a main general data frame. So this is first our data frame, and the next one we're going to save now is we're going to save our features data frame, and then we're now going to save our coefficient data frame. Okay. Now just observe what I'm going to do. Then after that, the last thing we're going to do now, we're going to save our best performing models. So how many of our models are best performing? We'll save them. Okay, not our pipeline. We can still save our pipeline, the pipeline that we scaled. Possible for us to save it because we did assign that as a pipeline model, pipeline class, or whatever stuff we want to call it. Okay, so yeah, that's it. So what we are going to do right now is we can now start by doing our DSCSV. So what we're going to call this, so anybody that is going to be watching this video, of course, you can get the data set, AMR pipeline. So I'm going to call it pipeline prediction dataset.csv. Okay. So we're going to save it as that. I think that's just it. So I'm just going to hit enter, and automatically that has saved. Now to check that, we can just click here and look at it. So this is our common separated file that we've been working with. This is 900 sheets. So you can actually see it. We've got gonorrhea, tuberculosis, lots of them, age and all of that. Now, if we don't want to have these ones here, what we can do is that, so what we can do actually, we can pass in, we can just pass in here, we can say index equals to none and save that still. So what happens that it automatically removes that index. Okay, so that is it. Now the next thing we're going to do now is we're going to save our features data frame. And what did we define our features data frame to be? We just want to save everything up because we might want to use them. Now we have two different feature data frame. We have our feature data frame for our tree, for our forest, and we have our data frame for our decision tree classifier. So both of them are what we can save. So we'll save for the first one. As usual, what we'll do is so I'm just going to save for our features data frame. I'm going to click that trees.df to CSV to underscore CSV. Then we'll pass it. What's going to be the name? We're going to call it features data frame. Then we'll call it for decision. I think I can start it with decision tree. Or that makes me decision tree features data frame. Okay, so we can leave it .csv. Then we can actually put the index equals to none. Or we can actually do the same thing for our decision tree. Okay, and then the next one we're going to do right now is we're not going to do for we're going to do for our random forest. So this is for our random, this is for random forest data frame. So we'll just rename this thing here to forest importance data frame. I think that's correct. Dot to CSV dot. I think I can just write here forest data frame, and I think I'll just click enter. So that's it. So this is our decision tree data frame, and this is our random forest data frame. Okay, now the last one is now how do we now, okay, for our coefficient data frame. So same thing is also going to happen, and I'm going to just go up. So just to be sure with the name that I gave for my coefficient data frame, and I said I call that log coefficient data frame, and I'm just going to go down and I'm just going to click on that dot to CSV. Then I'm going to pass it. I'm going to call it, I think this is correct now. Okay, yeah, so I'm just call it our logistic data frame. I'll call it .csv. You need to end it with this extension, because if you don't end it with this extension, it will not save as a comma separated value, and that's going to make it quite impossible for you to use for your data analysis or meta analysis. So I'm just going to hit that shit, and that enters immediately, and yeah, that's it. So the last one now is what are our best performing models. So we have two best performing models. Our decision tree classifier models, correctly labeled antimicrobial resistance data training. So essentially what we're going to do right now is we will need to now save that model, and what we're going to do now is we're going to save the model. Now remember, in programming I did explain in my previous video how to do file handling. And what do we do with file handling? We can say with open, right? We now pass in this method, so that's the open method. So we can now pass in the name of the file. So what's going to be the name of a file? Remember we imported pickle, which is what we wanted to use. And how many models are we saving? Because our pipeline performed well, our logistic regression was the least that performed, that's without scaling, and our as well as our decision tree and our random forest model all performed well. They performed well. So we'll now say logistic. No, we're going to say decision tree model dot pickle comma, we will say WB. So this is what we WB as F, or can call it as file. Okay. Now we'll now do pickle.dump. So we use the dump method. Now we'll pass inside the method that we want to save and file. So which of them are we saving now? So one of the first model that performed well is our log decision tree model. So this is the first model that performed well. Okay. Then the second model that we're going to save is our randomized forest classifier model. So I'm going to also save that, our random forest classifier model. Then the third one is our pipeline. The pipeline model. So that's the logistic regression after we scaled it. Okay. All right. So what we'll now do now is, now for our decision tree, we'll now go up. Where did we save the model? Remember when we returned it from this function, from this method, which I usually call the function. This is the model here, tree model. So we'll copy that. Okay. So we go down. So it's going to dump it. File. Sorry. I think that works. That works perfect. So I'm just going to enter that. Automatically, this is our decision tree model. Now we're going to do the same thing for our. Okay. So I'll just copy it down. Let's just type it again so that we'll practice. Okay. With open, then we'll now put our random forest model.pickle. Okay. Here I'm going to use as F. Okay. Then I'm going to do pickle.dump. Then I'll now pass in. That was our forest model, comma F. I'm going to do that, and automatically it has saved our random forest model. So if I actually want to check it, I can just open it as a text editor, and you're going to see the model. This is what it looks like. Then I can still do the same thing for decision tree model that we save. Now the idea behind saving the model is that we can always reuse them anytime that we want. And the last one I'm going to do now is the pipeline model, which I'm going to say with open, and I'm just going to try to save that. I'm going to say pipeline log. I'm just going to log pipeline model.pickle. Okay, come on. I'm going to do WB as F pickle.dump. So all these are models that finished with 100% accuracy, and I'm going to pass pipeline comma F, and I'm going to say that. Of course, that should save as well. So this is it, and I'm going to open that, and that's it. So guys, I want to actually really say a very big thank you to you all, everybody that stayed particularly to the part of this video. This is more it is what it is, and I want you to understand that machine learning is really very interesting. I'm going to drop the code, all of them, on my Git repository for you to access that, and I'm just going to run a bit of Git command here to show you also how that works. And I just wanted to make sure you practice. Remember, everything doesn't start in a day. It all starts by practice. And when you're consistent practicing, you're definitely going to be very good with programming, mathematics, statistics, and also some part of data analysis, which is something very much important. And it's not, there are a lot of documentations out there online. And for our new company, Synalytics, we'll be offering trainings from time to time on how to be very fantastic and great with programming. So that is going to be that for this session today. Basically, I've explained all of that. Which model was the best? I did do that. We did pipeline scaling. We had our reflection. We also created our feature importances and coefficients. We did our interpretation using our confusion matrix, precision score, recall score, and also we performed our model training using a blueprint class without any pipeline. We did our train test split, feature engineering, and we did our data preparation. So this is how we built our antimicrobial resistance prediction pipeline in machine learning. So I want to actually really thank you guys for your time. Just like I said before I end this session, I'm just going to commit this right away to my Git repository. You can follow me on Git, and basically I've got a lot of machine learning projects that I've committed on my Git. So that I have committed on my Git. I've committed a lot of these machine learning projects on my GitHub. So I think I'm just going to create one. I'm going to call this 20 ml. Then I think so we're going to actually like describe everything that we did today. This is let's say in this project, because we built a machine learning pipeline for it. And also we use the random forest. And perform scaling on our. So guys, this is the whole full description of this project. It's going to be public. I'm going to leave it public, and I'm just going to create that Git. So the first thing I'm going to do to commit this project. So the first thing I'm going to do to commit this project to Git is I'm going to initiate a Git command. I'm going to come here, and I'm going to press Ctrl tick. I'll say Git init. Then to initialize an empty repository. Everything here is untracked. I'm going to say git add space dot, and automatically it adds everything. Everything is now ready for staging. Then I'm now going to say git commit -m I'm going to call it initial commit. This is my initial commit. Okay, automatically it has now cleaned up everything, so it has saved these files now to my Git, to my local Git. Now for me to move it to my Git repository, I'm just going to copy this. I can say Git branch main, but that's I'm already on the main branch. As you can see, I'm already on the main branch, so you can see it here main. So I'm just going to hit that, and I think I can say the git push main origin. I think that works. Okay, no, I say git push origin main. I think that works perfect. Sorry, I just turned it upside down, and yeah, that works fine. So I think I can just you can check it out here to be sure that everything has committed. I can say git status and branch, nothing to commit, working tree clean. So I can go over to Git here, and I can just refresh this page, and automatically you can see all the projects. So you can click on the project. So this is the project, the AMR project. Yeah, this is it. This is the project, and you can click on it, and basically you can go through all the code that I have written, and we can also commit it. So you can see here I run all the code here, and so that's it. So guys, thank you very much for your time, and I want to actually really wish you well in your endeavors. I get everybody wants to learn programming, machine learning. Like I said, it's just a step at a time, and yeah, definitely you will get there. So see you in the next one, where I will be working on other projects. Bye bye.